everyone, thanks so much for clicking onto the video. We're going to be learning about Hess's law, and this is today's learning objective. And it's to be able to use Hess's law to perform calculations, including calculation of the enthalpy changes for reactions from enthalpies of combustion or from enthalpies of formation. Now I'm going to introduce Hess's law. And Hess's law states that the enthalpy change for a reaction is independent of the route taken. And what this basically means is that in any way you go from reactants to products, the enthalpy change will always be the same. So if we look at this example, it'll become a bit more clear. So the enthalpy change for the following reaction is minus 2,877 kilojoules per mole. Calculate the enthalpy change of formation of butane given the following data. So we're given the enthalpy changes of formation of carbon dioxide and water. And when you get a Hess's law question, it's good to set up a sort of diagram. So I like to put this equation at the top. So we have C4H10 gas plus 6.5 oxygens. And this forms 4 carbon dioxides and 5 waters. And now we can already see that this is an enthalpy change of combustion, because 1 mole of a fuel is being completely burned in oxygen to form carbon dioxide and water. But that's just extra information, so we don't actually need to think of that. So I like to put the minus 2877 in. So we've got minus 2,877. And this is the enthalpy change of combustion. And then we look at the question again. So you want the enthalpy change of formation of butane. And the definition for enthalpy change of formation is the enthalpy change when 1 mole is formed from its constituent elements in standard states and conditions, which means that the equation for the formation of butane should look like this. So you start off with 4 carbons, because we have got 4 carbons here. And then we would need 10, we've got 10 H atoms. So that means because the constituent element is hydrogen, which comes in 2s, because it's H2, then we would need 5 of them. So we would have 5 H2, and that would be a gas, because that's its standard state. And then that is now the enthalpy change of formation of butane. It would go like this. This would only form the butane though. So actually we add the 6.5 oxygens, and this actually doesn't do anything. So now we have some sort of diagram, and then we have a look at this bit here, and then we realize that this actually forms this. Because we have 4 carbons here, we have 8 oxygens plus 5 oxygens, and here we have 13 oxygens, like we do here, and we also have 10 hydrogens. So actually, this is the delta H of formation of all of this, whereas this will be equal to the enthalpy change of formation of just the butane, because the 6.5 oxygens haven't changed. So this is equal to the delta H of formation of the butane. And this is what we're trying to find. So this is the goal. And we're going from the start to the finish. So we can call this the start and we can call this the finish. Because no matter how we get to the finish, we should get the same enthalpy. So we know that we can go from this to this, and we already know this. We can work out this value from their given values, and then that means that if we go this way round, then we get an enthalpy change. But if we go this long way round here, then we should get the same enthalpy change. So that's the idea on how to work it out. So firstly, we're going to work out this delta H of formation from this to this. So the delta H of formation, that equals, it should be 4 times carbon dioxide because you're forming 4 of them. So it'd be 4 times minus 393. And then you would add on the waters. So each water, the enthalpy change is minus 286. Then you'd times that by 5. So 5 times minus 286. And this comes out to be minus 3002 kilojoules per mole. So we know that if we go this way around, we have this as an enthalpy change. So that means that if we go this way around, it has to also be equal to this. So what we do is, if we call this x, we now know that x minus 2877 has to equal minus 3002. And now we can just rearrange to find x. So x comes out to be minus 125 kilojoules per mole. Now we're going to look at a question. So feel free to click off the video and try it out for yourself first. So calculate the enthalpy change of combustion of ethene, C2H4, given these enthalpy changes of formation. So the first thing we do is we go back to the definition of enthalpy change of combustion. And it states that we start off with 1 mole of a substance, in this case ethene. We start off with C2H4 and we completely combust it. With oxygen, and everything is in standard states, and it's all measured under standard conditions. So those are the 3 things that we need to remember. So what is the equation for the enthalpy change of combustion of ethene? So we start off with ethene, and we completely combust it with oxygen. So this is a gas, so we combust it with oxygen, which is also a gas in its standard state. And this should form carbon dioxide and water, because we've gone through complete combustion. And now we just need to balance the equation. So we've got 2 carbons here, so I'm going to add a carbon there. And then we've got 2 hydrogens here, but 4 here, so I'm going to add a 2 here. And then I'm going to balance the waters. So I've got 2 here and 4 here, so that's 6. So we must have 3 oxygen molecules there. So this should be our delta H of combustion for ethene. So now we think about Hess's law, and we think that every route that I take will give me the same enthalpy. So we want this, but we're actually given enthalpy changes of formation. So the question must be wanting us to form these 2 things in order to find the delta H of combustion. So then we think about the definition of the enthalpy change of formation, and that's 1 mole of whatever it is that is formed, and it's from its constituent elements. and also in standard states. So now we think about the equation. So how do we form ethene? Well, we must have carbon. So we'll add a carbon, and that's a solid in its standard state. And then we must have hydrogens as well. And hydrogen in its standard state comes in a pair, so it exists as H2. So we must have a H2. And that's normally a gas in its standard state. And then I think about this oxygen. The way that we form this bit here, I would have to have oxygen. And if I want to form this, because we're given the enthalpy change of formation of ethene, that means that I can just add in this oxygen here, because it doesn't take any energy for me to change from 3 oxygens to 3 oxygens, because it's the same thing. So it won't make a difference if I add in 3 oxygens here. And then I have a look at this side. And actually all of these elements make this. So this must be another enthalpy change of formation. But first we're going to balance this equation. So we've got 2 carbons here, so we must have 2 carbons, and then 4 hydrogens, so we need 2 here, and then obviously this is already balanced. And if we look at the other side, it's balanced exactly the same. So now we know that this reaction here is the delta H of formation of everything, and this is the delta H of formation of the ethene. So now we think about where's the start and where's the finish. So we're trying to work out this. We know this, and we can work out this, which means that we could call this the start and this the finish, because we know what the enthalpy is when we go this way, and we can work out what the enthalpy is when we go this way by adding this and this. And so we can find this by minusing this from this. So first we're going to work out the delta H of formation of this reaction. So if we go back to the question, we have that C2H4 is the 52. That's minus 393 and minus 286. Okay, so for this bit, you would have 2 times, so the delta H of formation equals 2 times the minus 393. And then you'd add on 2 times minus 286. And that gives you minus 1,358 kilojoules per mole. And then you do the same thing for this bit, but actually it already gives it to you in the question. If we scroll up, it gives you the 52 kilojoules per mole. So we already know that this is plus 52 kilojoules per mole. So if we call this x because we don't know it, and then we use these two, we then have delta HF of C2H4 plus x equals the delta H of formation of this bit. So we then have plus 52 plus x equals minus 1358. And then you rearrange to find x. So x turns out to be minus 1,410 kilojoules per mole. And one way to check whether you have done it right is that you've got minus sign here, because combustion is exothermic, because heat is given out. So this should be a minus sign. So if you've got a positive sign, then it kind of indicates that something has gone wrong along the way. Hi everyone, thanks so much for joining this video. Today we're going to look at some harder questions using Hess's law. So the first question says to calculate the standard enthalpy change for the following reaction using the enthalpy changes given. So what I like to do first is to write out the equations for combustion and for formation, so I know exactly what I've got. So the enthalpy of combustion of sulfur, the enthalpy of combustion is when you completely combust 1 mole of the thing you're finding the enthalpy change for. So that means that we have 1 mole of sulfur and we completely combust it in oxygen, and these are in their standard states, to form sulfur dioxide. And this is actually already balanced, so this would be my equation. And then we look at the formation of water and of H2S. So the enthalpy change of formation is the enthalpy change when 1 mole of the thing we want is formed. So that means that 1 mole of water is formed. And so from its constituent elements, we need to form 1 mole of water. So using hydrogen in its standard state and oxygen in its standard state, we need to form 1 mole of water in its standard state. And that means that we must have half of an oxygen because now it's balanced. You need to remember not to put any numbers before the water, because the whole point of the enthalpy change of formation is that 1 mole is formed. So if you change that, then it won't work. And then for H2S, so making it out of hydrogen gas again, and then plus sulfur, which is solid, and then we need to form H2S, which is a gas. And as you can see, this one's already balanced, so this will be the equation. And now we have a look at how we can combine these all together to find the delta H of this reaction. And so first I like to write out this equation, plus 2H2S gas, and I call this the enthalpy change of reaction. Okay, and now we can see that the sulfur and the oxygen, I can combust the sulfur to form sulfur dioxide. So if we have a sulfur here and add it with an oxygen, we can form this sulfur dioxide. And then with this hydrogen sulfide, we can form it using hydrogen and sulfur. So if I add a hydrogen and a sulfur, then we can form hydrogen sulfide. But then we've got 2 hydrogen sulfides, so that means we need 2 of the H2 and 2 of the sulfur. And then looking at this bit, we now have balanced this equation as well. So we've got 1 sulfur here and 2 sulfurs here. So the enthalpy of formation of this sulfur is 0 because we already have the same thing here. And then we have oxygen and water, and this will form the 2 waters here because this is the equation for the enthalpy of formation, but we've got double that amount, so it all works out. So here we have the enthalpy of formation of the 2 H2Os, and then here we have the delta H of combustion of the sulfur, and we have the delta H of formation of the 2 H2S's. And now we can work out what we know and what we don't know. So the delta H of combustion of sulfur we know is minus 297. So we can work this out as minus 297, and then you plus 2 times the formation of H2S, which is minus 20. And this turns out to be minus 337 kilojoules per mole. And now we work out this enthalpy of formation of the two waters. So we would do 2 times, and 1 water is minus 286. So we do 2 times this, and this equals minus 572 kilojoules per mole. And after we work these two out, we then have a look at the diagram and see how we can find this enthalpy change of reaction. So Hess's law states that the enthalpy change is independent of whichever route you take from start to finish. So if we call this the start and this the finish, then that means that if we go this way round, the enthalpy change will be exactly the same as if we went all the way round. And because we know this and we know this, we can then find the enthalpy change of reaction. So if I label this X, this way we would have minus 572, and that should be equal to, this is minus 337 plus X. And so rearranging for X, we can then find the enthalpy change of reaction. So X turns out to be minus 235 kilojoules per mole. So the enthalpy change of reaction is minus 235 kilojoules per mole. So before I start on the second question, feel free to pause the video and try it yourself first. So calculate the enthalpy of combustion of CS2 given the following enthalpy changes. Now first I start off by writing the equation for the enthalpy of combustion of CS2. So we know that 1 mole of CS2 is being combusted, fully combusted with oxygen. So it goes to completion. So we form carbon dioxide gas and also sulfur dioxide gas. And now we just need to balance it. So we can't change this because it's in the definition that we're combusting 1 mole. So that must mean we have 2 sulfurs. So if I add a 2 here, we then get a balanced equation if I balance the oxygens. So we have 4 oxygens plus 2, so that's 6. So we need 6 on this side, and we've only got 2, so that means we need 3 oxygen molecules. And this is the delta H of combustion of the CS2. And now we have a look at what we have. And so we have the enthalpy of combustion of the carbon and the sulfur. And then we have the formation of CS2. So that means that we can add the constituent elements of CS2 together to form CS2. But the definition of enthalpy change of formation is that it's the enthalpy change when 1 mole is formed. So we need to form 1 mole of this. So we need to balance this so that I have 2 sulfurs here. And so this is now forming this. And then we can combust carbon. So if I add an oxygen here, we can form the carbon dioxide because I'm completely combusting 1 mole with oxygen to form carbon dioxide. And then the same with the sulfur dioxide. So I can combust sulfur with oxygen completely to form sulfur dioxide. So then I can add on, well, normally it would be sulfur plus oxygen goes to form sulfur dioxide, but because we have 2 moles here, we need to double the amount of everything. We've already got 2 sulfurs here, so we need 2 oxygens. And so now this will be the enthalpy change of formation of the CS2, and this will be the delta H of combustion of the carbon and also the delta H of combustion of the sulfur. And now we work out all these numbers. So the delta H formation of CS2 is plus 88. And here we have minus 393 plus minus 297. You need to times by 2 actually. So it would be 2 times minus 297. And when you add these together, you get minus 987 kilojoules per mole. And now you think back to the diagram again, and you have a look to see where I could start and where I could finish. So I think I can start here, and I can finish here, because we know what this is. So we know the enthalpy change when we go this way, and we can work out what the enthalpy change this way, because it'll be exactly the same as this. And so we can work out this enthalpy change of combustion. So then we have minus 987 equals 88 plus the delta H of combustion. So then we rearrange to find the delta H of combustion, and that equals minus 1075 kilojoules per mole.